This video is for The Living Earth, Unit 2.5. Today's essential question: how do mechanical and chemical weathering change Earth's surface? Our first main idea: mechanical weathering. Mechanical weathering is the natural breakdown of rock into sediments by physical changes. Mechanical weathering is sometimes also referred to as physical weathering. Causes of mechanical weathering are ice wedging and root growth. Ice wedging occurs during cycles of melting and freezing as temperatures change daily or seasonally. When liquid water freezes, it expands in volume by about 10%. When liquid water seeps into cracks in rocks and then freezes, the expansion of the rock is a force powerful enough to crack the rock further. When temperatures rise and the ice melts, the resulting water seeps deeper into those cracks. Freezing continues the cycle by further expanding the cracks. Eventually, the cracks cause rock to crumble away. Root growth is another major cause of mechanical weathering. Tree roots grow down into cracks in bedrock, and as a tree grows, its roots thicken, causing the cracks to widen. Tree roots continually delve deeper into the ground in search of water, further widening cracks in the rock. Other causes of mechanical weathering include abrasion, impacts, and exfoliation. Abrasion is the scouring or scraping of rock, usually caused by the action of glaciers as they creep slowly down the mountains or by friction with wind-blown sand. Impacts of meteorites can blow rock into bits and form craters. Exfoliation is a type of weathering in which thin layers of rock peel off exposed rock surfaces like slivers of onion. This typically happens to bedrock that has been buried underneath other layers of rock. If the rock expands, the cracks appear in its surface, weakening the rock so that its outer layer may be stripped away one by one. Our next main idea: the properties of water. Water is found almost everywhere on Earth, in the oceans, lakes, rivers, and ponds. Water is a compound consisting of hydrogen and oxygen atoms bonded together. In water molecules, 2 atoms of hydrogen and 1 atom of oxygen are, in fact, bonded together. Water has several physical and chemical properties that make it a unique substance. These properties include water's exceptional capacity to absorb, store, and release large amounts of energy as it changes state. Water is able also to transmit sunlight, to expand on freezing, and to dissolve and transport numerous materials. It also lowers the viscosity and melting points of rocks when mixed with the hot solid rock in Earth's mantle. Each of these properties play a role in how water affects most natural processes on Earth, such as ice wedging, which contributes to mechanical weathering, and the ocean's thermal capacity to balance temperature differences. Water exists in 3 states: as solid, liquid, and gas. As liquid water, it carries soil and rocks from one place to another, and it supports a variety of life forms that live on the Earth. Water is found as a gas, which is called water vapor also, and also, in addition, as ice crystals high in the atmosphere. It remains suspended as droplets in clouds, then falls as precipitation, or rests as solid ice on the tops of mountains or in glaciers. Energy from the sun causes evaporation, and gravitational force and Earth's rotation propel oceanic and atmospheric circulation, which in turn transports water around the globe through the water cycle. About 97% of Earth's water is salt water and can be found in an ocean or in a saltwater lake. The remaining 3% is fresh water, which accumulates in glaciers, underground aquifers, streams, bays, and freshwater lakes as well as rivers. Water is considered a significant factor in the mechanical weathering of Earth's crust. For example, liquid water flows downhill, or it turns to solid ice, and it changes the landscape in which it occurs by breaking down rock materials into sediments. The physical properties of water include polarity, which causes adhesion and cohesion, as well as capillary action. Other properties include density and color. Water's chemical properties, such as conductivity and pH, on the other hand, are the basis of chemical weathering. Our second main idea, chemical weathering.
Now on to chemical weathering. Chemical weathering decomposes rock and minerals through chemical reactions between the rock and its environment. Chemical weathering processes include dissolution, oxidation, and hydrolysis.
Dissolution is the breakdown of minerals into their component elements. Most minerals don't dissolve very much in pure water, but add a little acid to that water and much more mineral dissolves. As minerals break down and dissolve in the presence of acid, the rocks break down too. Limestone just flat out dissolves in the presence of acid, so acid rain has caused some serious destruction of limestone.
The next process, oxidation, is really just rusting. Oxidation is a reaction involving oxygen, often oxygen dissolved in water. Oxidation contributes a lot to the weathering of ferromagnesian minerals like olivine and pyroxene. Remember, ferromagnesian minerals are mafic, containing plenty of iron and magnesium.
The iron in these minerals react with oxygen to form a reddish-brown oxide called hematite, or a yellowish-brown hydroxide called limonite. Reddish soils and sedimentary rocks may contain small bits of hematite or limonite.
Oxidation is the chemical process most likely to weather iron-containing minerals. Minerals containing lots of silica, on the other hand, are most likely dissolved by a process called hydrolysis.
Hydrolysis is a special kind of dissolution reaction in which excess protons or hydroxyl ions are left in a solution at the end of the reaction. In short, hydrolysis is just the term for the reaction of a mineral with water.
That's easy to remember because you probably know that hydro means water. The positive hydrogen ions and the negative hydroxyl ions in water react with the ions in the minerals. During hydrolysis, positive hydrogen ions actually replace the positive ions in the minerals, changing the mineral's composition. The negative hydroxyl ions just get left behind in the solution. Like we said, this reaction happens most often with silicates like feldspar. Hydrolysis breaks down feldspar into
Now on to chemical weathering.
Our last main idea, rates of weathering. Although the breakdown of rock is generally a slow process, in some cases it can proceed more quickly. The rate of speed at which weathering occurs depends on many variables, such as the composition of the rock, meaning what is the rock made of, the rock's surface area that is exposed to air and water, climate conditions, including the humidity and temperature of the area, the shape of the landscape, which is known as topography, elevation, and then the actions of living organisms. Mechanical and chemical weathering are also key processes in the functioning of the rock cycle. Sometimes, different rocks in the same landform weather at different rates. This is called differential weathering. Differential weathering can sometimes produce dramatic sculpture-like effects, such as the stone arches that dot the western United States. This type of weathering can be both chemical and mechanical.
What could be more permanent than a massive mountain range? cliffs along a shoreline seem eternal. Extensive plains look like they have always been there. And yet, all of these landforms are constantly being changed and modified by the forces of weathering and erosion. As you watch this program, think about, how do weathering and erosion reshape the landscape? Weathering is the wearing down of rocks, while erosion occurs when the weathered particles are carried away and deposited in another location. Both weathering and erosion can be caused by the wind, which can pick up soil or sand and blow it long distances. But a much more common agent is water. Weathering involves two processes that work together to decompose rock on the surface. Mechanical weathering is the physical breakup of rocks. When it rains, water seeps into the crevices of rocks. As water freezes, it expands in volume by about 10%. In cold climates, over the course of the winter, water can freeze and thaw several times. Each time, it puts pressure on the rocks and finally splits them apart. Glaciers are also powerful agents of mechanical weathering. All glaciers slowly move and flow. They grind against the bedrock and break up vast quantities of rock. The impact of glaciers can be seen on the landscape after they retreat. Where glaciers paused for a time, they have left behind hills of rock and sand called moraines, or glacial till. Chemical weathering involves the chemical change of the minerals in the rocks. Water is a mild solvent, and rainwater falling on the rock will dissolve microscopic particles. Some rocks, like granite, are very hard, and little is dissolved. But others, like limestone, dissolve easily. Water contains dissolved oxygen. When it comes in contact with iron, a common mineral in rocks, the oxygen combines with the iron to produce iron oxide, or rust. This weakens the rock. The same chemical process occurs when water comes in contact with iron or steel. If exposed to the weather, it does not take long before these metals are covered with rust. Rainwater often contains a weak solution of sulfuric acid, which wears away some types of rocks. It is called acid rain. These statues have been worn away so much, they have almost completely lost their features. Mechanical and chemical weathering act in combination. In colder climates, mechanical weathering has a greater impact. And in warmer climates, chemical weathering plays a more important role in breaking down rocks. But both are important in the weathering process.
At this point, you should be able to generate a full and complete response to today's essential question. How do mechanical and chemical weathering change Earth's surface?